Okay, so here's a target function. You want to maximize or minimize x squared plus 4y squared plus 4z squared under this condition. Now, one thing that may not be apparent to you when you first solve this question, but if you think a little bit, you'll see that the maximum value of this is actually the maximum value of this function doesn't actually exist. The reason is you can set z at 0 and to get rid of it, and then you can make x to be a really, really large positive value, whereas y has some really big negative value. To still manage to make 7. So what's an example? Oh, here's an example. You could make x to be 3.5 so that it matches with that, and make y as a million and z as negative million. This is an example that satisfies this condition, right?
Yeah.
You agree?
Mm-hmm.
And if you plug these into this function, what do you get? This will be like 4 trillion, 8 trillion, and something, right? So you get huge, huge values for this while satisfying this. Okay? So that means, and this gate can be played by putting more zeros, and you can make this as large as possible. So actually, although the question is phrased this way, you can verify that it doesn't have a maximum. So what it actually has is just the minimum. Solution. Max doesn't exist. For the min, we have to use the Lagrange multiplier, right? So what's the Lagrange multiplier? Lagrange of f. That's 2x,
8y,
8y, 8z, and Lagrange of g, gradient of g, sorry. Gradient of f, gradient of g is
2, 4,
2, 4. Now where would you multiply lambda?
g.
This time to this one because this is simpler, right? So we have 2x, 8y, 8z equal to lambda times 2, 4, 4. So that 2x is equal to 2 times lambda. And then 8y is equal to 4 lambda. 8z is equal to 4 lambda. Giving you x equal to lambda, y equals to lambda over 2, z equal to lambda over. Okay, now what? Plug it into the constraint. Okay, if you don't use the constraint, you're not doing it right. So you plug it into the constraint, and we get 2 times lambda plus 2 times lambda plus 2 times lambda equal to 7, giving you lambda equals to 7 over 6. Okay. And once you get lambda equal to 7 over 6, then you can plug it back in here to get, so lambda equal to 7 over 6 gives you x equal to 7 over 6, y equal to 7 over 12, z equal to 7 over 12. And then we know that we know that at 7 over 6, 7 over 12, 7 over 12, the x squared plus 4y squared plus 4z squared is maximized. That's what we figure out. So we plug them in. So what's the not maximized? We just figured out that there's no maximized. It's minimized, right? So so it must be the minimum because there's no maximum. It must have the minimum. Now, and by the way, we know that this has a minimum because it has to be positive or 0, right? So it can't be negative. So it must have something that's tried to get near 0. And what if you add this condition, it's impossible to become 0. You can check that too. All right, so let's evaluate this function. So, which is 7 over 6 squared, 7 over 12 squared times 4, 7 over 12 squared times 4, and that's 49 over 36, 49 over 12, is that right?
Mm-hmm.
Yeah.
Should be 245 over 6. Wait.
Right? It's 144 and 4, so it's 36. All of them gives you 49 over 36 if you put them in.
Only one of them equals. Well, the second and third equals 49 over 12.
I got 196.
Say that again, what did you get?
So the first one squared would be 49 over 12, right?
No, 36. 6 squared is 36, right?
Yeah.
Oh, okay. I don't know its fractions then.
It's 49 over 144 times 4. 49 over 144 times 4.
And yes, it is 49 over 12.
Yeah, so it's 49 over 12, right? Okay, that's how I do it. Could you